Welcome to this comprehensive guide on managing game states in a mini action game, using design patterns within Unity 3D and Visual Studio. This tutorial will equip you with the foundational knowledge and practical skills to implement robust state management systems in your own projects, ensuring your games are both dynamic and responsive. This tutorial is specifically designed for beginner game developers, providing a step-by-step approach to understanding and implementing robust state management. We will break down complex concepts into easily digestible parts, making it accessible even if you're new to game development or state machines. Effective state management is crucial for creating dynamic and responsive games, allowing you to control player actions, enemy behaviors, and level progression seamlessly. Without proper state management, your game logic can quickly become tangled and difficult to maintain, leading to bugs and development slowdowns. We'll begin by defining what a game state is and why it's essential for any game, especially in an action-oriented title where timing and responsiveness are key. A game state essentially describes the current condition or mode of a game entity or the game as a whole, dictating its behavior and interactions. Our focus will be on implementing the state design pattern, a powerful tool for encapsulating state-specific behaviors and making your code more modular and maintainable. This pattern allows an object to alter its behavior when its internal state changes, making it appear as if the object has changed its class. First, let's set up our Unity project. Open Unity Hub and create a new 3D project, naming it Mini Action Game. This initial setup is vital for ensuring a clean and organized development environment, which will benefit us throughout the entire project. Once the project loads, we'll organize our assets by creating a scripts folder and a prefabs folder to keep everything tidy. Good folder structure is a cornerstone of efficient game development, preventing clutter and making assets easy to locate and manage. Now, let's dive into Visual Studio to define our base state interface. This interface will outline the common methods all our game states will implement, providing a standardized contract for how states should behave and interact within our state machine system. We'll create an interface called iState with methods like enter, execute, and exit. These methods will be called when a state is entered, updated, or exited, respectively. The enter method initializes the state, execute handles continuous logic, and exit cleans up when leaving the state. Next, we'll implement a state machine class. This class will manage the current state and handle transitions between different states. It acts as the central orchestrator, ensuring that only one state is active at a time and facilitating smooth transitions based on game logic. The state machine will have a change state method that takes an iState object, calls the exit method of the current state, and then the enter method of the new state. This methodical approach ensures that states are properly initialized and deinitialized, preventing unexpected behavior. Tip: always ensure your change state method handles null checks for the current state to prevent errors when transitioning from an initial null state. This small but crucial detail can save you from frustrating runtime exceptions, especially at the start of your game or when resetting states. Now, let's apply this to our player character. We'll define several player states, such as player idle state, player moving state, and player attacking state. Each of these states will encapsulate the unique behaviors and animations associated with that particular player action. Create a new C# script in Unity called Player Controller and attach it to your player game object. This script will hold our state machine instance, acting as the bridge between our player character and the state management system we are building. Inside Player Controller, initialize the state machine and set the initial state, for example, player idle state, in the start method. This ensures that our player character begins in a defined state as soon as the game starts, ready to respond to player input. Each player state class will inherit from iState and implement its enter, execute, and exit methods, defining specific behaviors for that state. This adherence to the iState interface guarantees consistency and proper functionality across all player states. For player idle state, execute might check for input to transition to player moving state or player attacking state. This is where the state machine truly shines, allowing for clear, condition-based transitions between different player behaviors. In player moving state, the execute method will handle player movement logic, while exit might stop any movement animations. This separation of concerns keeps the code clean and makes it easy to modify movement or animation behaviors without affecting other states. Tip: keep your state classes focused. Each state should only be responsible for its specific behavior, avoiding unnecessary complexity. Overloading a state with too many responsibilities can lead to a God state anti-pattern, making your system harder to manage. Now, let's consider enemy states. Enemies often have more complex behaviors, such as enemy patrol state, enemy chase state, and enemy attack state. Managing these distinct behaviors with a state machine provides a clear and organized way to define enemy AI. Similar to the player, we'll create an enemy controller script and attach it to our enemy game object, managing its own state machine. This allows each enemy to independently manage its behavior, leading to more dynamic and believable AI. The enemy patrol state execute method will contain logic for moving between predefined waypoints. This state defines the enemy's default, non-aggressive behavior, ensuring it covers its designated area until a threat is detected. When the player enters a certain range, the enemy patrol state can transition to enemy chase state. This transition is triggered by a specific condition, demonstrating how external events can influence state changes within our system. The enemy chase state will then update the enemy's movement to follow the player, and enemy attack state will handle attack animations and damage application. These states work in sequence, allowing the enemy to react dynamically to the player's presence and engage in combat. Tip: use Unity's gizmos to visualize enemy patrol paths or detection ranges directly in the scene view for easier debugging. This visual feedback is invaluable for understanding and fine-tuning AI behavior without constantly running the game. Finally, let's consider level states. This could include level loading state, level playing state, level paused state, and level game over state. Managing the overall flow of your game through level states provides a robust framework for handling different game phases. Create a level manager game object in your scene and attach a level manager script to it. This will manage the overall game flow, acting as the central control point for the entire game state, from loading to game over. The level loading state would handle asynchronous scene loading and displaying a loading screen. This state ensures a smooth user experience by managing the transition between different game scenes and providing visual feedback during loading. Once loading is complete, it transitions to level playing state, where all game logic, player input, and enemy AI are active. This is the core gameplay state where players interact with the game world and experience the action. The level pause state would pause game time, display a pause menu, and disable player input. This state is crucial for providing players with control over their game experience, allowing them to take breaks or adjust settings. When the player's health reaches 0, the level playing state transitions to level game over state, displaying the game over screen. This state signifies the end of a game session, providing options like restarting or returning to the main menu. Tip: for level states, consider using Unity's time.timescale equals 0f to pause the game and time.timescale equals 1f to resume. This simple yet effective method allows you to halt all time-dependent operations, creating a true pause effect. To make state transitions more dynamic, you can pass data between states. For instance, passing the player's last known position to an enemy's chase state. This allows the new state to immediately act upon relevant information from the previous state. This allows states to be more context-aware and reduces the need for states to directly access components they shouldn't be responsible for. By passing data, you maintain a cleaner separation of concerns and improve the modularity of your state machine. Another advanced technique is using a stack-based state machine for managing UI or nested states, allowing you to push and pop states. This approach is particularly useful when you have hierarchical states, where one state can temporarily suspend another. This is particularly useful for menus where you might open a submenu and then return to the previous menu without losing its context. For example, opening an options menu from the main menu, then a video settings menu from options, and seamlessly returning through each. Tip: while powerful, avoid over-engineering. Start with a simple state machine and only introduce more complex patterns like stack-based ones when necessary. Simplicity often leads to more robust and easier to maintain code in the long run. Remember to thoroughly test your state transitions. Play through your game and intentionally try to break the state logic to find edge cases. Rigorous testing helps uncover unexpected behaviors and ensures your state machine is resilient. Debugging state machines can be challenging, so consider adding debug logs in your enter and exit methods to track state changes in the console. These logs provide a clear timeline of state transitions, making it much easier to pinpoint issues. You can also create custom Unity editor tools to visualize the current state of your game objects, providing immediate feedback during development. Visualizing states directly in the editor can dramatically speed up debugging and understanding complex state interactions. By consistently applying the state design pattern, you'll build a robust and scalable foundation for your game's logic, making future development much smoother. This architectural approach promotes clarity and reduces the likelihood of introducing new bugs with each feature. This approach not only improves code readability and maintainability, but also makes it easier to introduce new features or modify existing behaviors without breaking other parts of your game. It fosters a modular codebase where changes are localized and predictable. We've covered the fundamentals of implementing state machines for player, enemy, and level management in Unity 3D using Visual Studio. You now have a solid understanding of how to structure your game logic using this powerful design pattern. Experiment with these concepts, adapt them to your own projects, and continue exploring more advanced state management techniques. The journey of game development is one of continuous learning and application, and state machines are a fundamental tool in your arsenal. Thank you for watching, and happy game developing. We hope this tutorial has provided you with valuable insights and practical skills to enhance your game development projects.